Let's start talking about the material in section 3.1. The material in 3.1 is actually just a little bit more information about instantaneous rates of change and a little terminology. I thought we'd start by a brief review of average rates of change and instantaneous rates of change. To find the average rate of change of a function over a closed interval, we simply compute a slope. So if I have this function y equals f of x, and let's see, this is the point a comma f of a, and this is the point b comma f of b, the average rate of change is simply the slope found going through those 2 points, the slope of a secant line. All right, so I need to find that slope. Slopes always rise over run, the change in y, f of b minus f of a, all over b minus a. And that would be my average rate of change. And so now the idea is we ask the question, well, instead of knowing the average rate of change between a and b, what if I wanted to know the actual instantaneous rate of change at just a, how fast something is moving at a specific value in the domain? So let's imagine I have that same function, y equals f of x, and I have that same spot marked here. But this time, instead of calling it b, I'm going to imagine that I let b equal a plus h, where h is just the distance between a and b, right? So if h is that distance, then b becomes a plus h, and then this y value up here would be f of a plus h. In other words, we can translate between these two pictures by saying, well, just let b equal a plus h, where h is just some distance. The slope of that secant line would then be f of a plus h minus f of a all over. And then a plus h minus a just gives me that distance h. And that's going to be important. That value of h, it's the distance between these two values in the domain. It's the change in x. And then I say, well, that would still be an average rate of change. That would be one of these. Even if I imagined letting h get smaller, right? I'm always getting an average rate of change. And what I want to know is how fast I'm moving just right here. And so the idea is I don't just need to let h get small. I need to let h go to 0. And so this slope of my tangent line, this instantaneous rate of change, I have to take a limit as h approaches 0. All right, so this limit, provided it exists, is the instantaneous rate of change. This calculation in the middle is called the difference quotient, and so my instantaneous rate of change is the limit of the difference quotient. And I should be a little more specific here. This is an instantaneous rate of change at x equals a. A is a value in my domain, and h is a distance. And this is a two-side limit. My picture here, I'm imagining that h is getting closer to 0 from the right-hand side, but for this limit to exist, I'd have to think about getting the same value as h approached a from the left. Another way to say that is I could draw this picture with a and b reversed, right, and look at secant lines on the other side. All right, so my instantaneous rate of change, the limit of a difference quotient. Let's see if we can look at that just a little bit more. So I'm going to write down the first definition from your textbook that is in chapter 3.1. The slope of the curve y equals f of x at the point a comma f of a is the number the limit as h approaches 0, f of a plus h minus f of a all over h, with the note that that's only true if that limit exists. Okay, the slope of the curve at a point is the limit of the difference quotient. Now look at that definition, I say, well, that's just the slope of my tangent line. That's just the instantaneous rate of change. And so all of a sudden I realize that there's just more than one way of saying all of these things. And then we could go on to say the tangent line to y equals f of x at x equals a is the line that passes through a comma f of a with slope, and it's this slope. I have to match that. So I'm going to write that down here even though I'm running out of room. Well, all this sentence does is it kind of combines the two ideas, or the three ideas. This limit, when it exists, is called the instantaneous rate of change. It's also called the slope of the curve. It's also the slope of a tangent line. And we're going to have one more name for that in a minute, but I thought we'd take this moment just to do an example. Find the slope of the curve y equals 2 over x at x equals 1. Okay, find the slope of the curve at the point x equals 1 in the domain. Well, what I'm thinking is I just need to find the slope of my tangent line, or the instantaneous rate of change. I need to evaluate this limit. So I have my function and I have a value for x. So this is 2 over a plus h goes in for x minus f of a, and if I plug a 2 in, if I plug a 1 in for x, I just get the real number 2 all over h. All right, well, as h is tending towards 0, if I tried to evaluate this right now, I would get 0 on the bottom of this fraction. So I need to do some algebra here. Better than that, though, if I plug 0 into the top, it's a 0 over 0. It's one of those things where I think if I do enough algebra, I'll probably be able to cancel something out. So I'm just going to do a fraction trick. I'm going to multiply the top and bottom by 1 plus h. Clearing my fraction, my big fraction of the little fractions, making this not such a compounded fraction. I need to distribute on the top, still taking the limit as h approaches 0. Here the 1 plus h is canceled, and here I have minus 2 times 1 plus h, and on the bottom, h times 1 plus h. Notice I didn't multiply that out. I left it factored. And if I go back to the start here, right, I have one of those 0 over zeros. I need to cancel an h out of both places, or at least that's what I'm hoping to do. So I'm not going to multiply the bottom out when I'm using a trick like this. In fact, I never will. I'm trying to cancel that h off, so I'm going to leave it factored. If I multiplied it out, it's not that I'm wrong. I'm just going to end up having to factor it back out later. All right, so just continuing up here, I have a limit as h approaches 0. On the top, I need to distribute 2 minus 2h. All right, continuing on, I see that those 2's cancel here. I have minus 2h over h times 1 plus h. And here's that most important moment where I get to cancel an h out of both places. That was what was keeping me from evaluating this limit. So now I have minus 2 over 1 plus h, and I can evaluate this limit now. I'll get a minus 2 over 1 is minus 2. The slope of the curve, not the slope, the slope of the curve at x equals 1 is minus 2. All right, and this was a fine answer. I just felt like writing it out in that very tiny box here, and that's all I need. I wasn't asked to find the equation of a tangent line. If I was, I would take that slope and look at the point 1 comma 2 and find the equation of that line. All right, so I found the slope of that curve. I feel like that's a good spot to end this video. Go on to the next video when you're ready, and we're going to define something super important for a calculus class.